1961. He did his postgraduate studies in England and then immigrated to Canada and practiced this orthopedic surgery in conjunction with family practice in Truro, this Nova Scotia, a small town, as was the style of practice in small town Canada. Because of his interest in computing, he developed a computer language APL and did work for Canadian International Development Agency (CIDA), traveling and teaching in China and Zimbabwe and writing software projects for government of Nova Scotia and government of Ontario. His latest project is a new computer language called Ganit for India and Indian children who do not understand English. He is Jain by birth and conviction. He is married and his nurse wife, having retired from active nursing now, teaches personal support workers, PSWs in Toronto. Her students are often new immigrants from India. He has two grown-up daughters. Dr. and Mrs. Mehta live with Moneesha, the elder daughter, in Toronto. At the daughter's insistence, he got interested in genetics approach to medicine in 2019, and in 2020 took a detailed course in genetics, a connection to diet and health, with certification from University of Toronto. He has already given a talk on the subject to JAS. And about Miss Moneesha Mehta graduated with master degree in mathematics, this Dalhousie University, Nova Scotia, and also a teaching degree B.Ed from the most prestigious Canadian university, Mount Allison University, for this kind of work in New Brunswick. She has also traveled the world, having done some time studying under famous classical singer Padma Talwalkar. Padma Talwalkar, 1992 in Bombay. She worked briefly in America, Holland, and England. She did some teaching, but later shifted into computing and data analysis work with Cisco, then with Rogers and IBM. Her last job was with Hitachi Ventura, and she currently works for a Canadian Border Services Agency. She is interested in music and in computer and human languages and has been a major help to her father in the development of computer language Ganit. When Dr. Mehta wrote the preliminary draft of today's presentation, mathematical representation of Shadwat, she came up with many modifications and additions. Therefore, this can be considered more her effort than Dr. Mehta's. So I invite first Dr. Navin Mehta to start his lecture, his webinar. Dr. Navin Mehta.
Thank you for giving me time on this August body. Let's have the slides, please. Moneesha. Next. We plan to show some fun, interesting mathematical interpretation of the Shadwat. We do not claim that these are the originally intended interpretations, nor even that they are in any sense correct. We simply present them as interesting point of view that these 7 truths as laid out in Shadwat lend themselves peculiarly well to mathematical and logical interpretation. So well, indeed, that it seems highly probable that they're meant to have some kind of logical interpretation.
Are there some problem here?
Next.
So we just want to point out that the interpretations of any words in an ancient language can be very different from person to person and time to time. Language and meaning of words change naturally over the centuries and millennia. And ancient texts were, of course, passed on verbally for centuries before being written down. So we can expect many changes and variations. And in any case, one word can have more than one meaning. at the same time. So based on our research, we made some of our own interpretations of the words in Syadvad, but we don't claim that these are the only possible interpretations.
Meaning of Syad. Although some people have translated Syad as maybe, we take it to mean in truth, or in reality, or really, or relatively true. For example, meaning of Syadvad explained by a Jain guru in this particular URL I have on the screen, the link, YouTube. He definitely denies the translation of the word Syad as maybe, and indicates clearly that the Syadvad refers to different ways of looking at reality. Relative to one person, a statement X might be true, but relative to another, X might be false. Now we are still discussing the scriptural meaning. In another link I've given, Kritam Kimapi Neva Syad means no action is ever committed in reality. In this meaning of Syad, we are continuing to explain Acharya Mahaprabhu's blog. He says very clearly the Sanskrit verse, Nimantrit Syad Vardhavya Rog Api Nimantrita Animantran Vigyanam Gyanam Buddha Edam. Meaning, senility comes uninvited, disease comes invited too. Uninvited science is called knowledge in the wise ones. This verse also emphasizes that there is no maybe, but different alternatives of reality.
The other words, of course, are asti, which means existent or present, nasti, which means not present or not existent, so opposite of asti, and cha, it means and, both also, moreover. Avaktavyam is indescribable or infinite, perhaps unknown, and Dad will explain a little bit more about the roots of that word.
Vakta means shown, described, countable. Vaktavya means fit to be said, told, spoken, or declared describable. Tattarhi kavat vaktavya na vaktavyam. That's occurring in Mahabharata frequently. And then indicates not or opposite of that. So avaktavyam negates the meaning of vaktavya and becomes indescribable, not showable, infinite. Infinite, I will specifically try to emphasize. Unknown as quantity. Syad asti, English pronunciation. English translation is really it is, it exists, is present. Associated truth value is called true in a bipolar way of representing it. Syadnasti, reality is not, it does not exist, it's absent. In bipolar way of saying it's false. Syad asti nasticha. Reality it is and it is not. True and false. Syad avaktavyam. Reality it is indeterminate, unknown, indeterminate. Syad asti avaktavyam cha. Reality it is and indeterminate. True and unknown. Syat nasti cha avaktavyam cha. Reality it is not and it is indeterminate, false and unknown. Syat asti cha nasti cha avyaktam cha. Really it is not, and it is in the true and false and unknown. These are the 7 truths that are the current way of this description in the scriptures.
We'll just explain these 7 truths a little bit in English. And again, we're not saying that this is the explanation, but this is sort of one understanding of it. So, and in particular, we're looking at the truth values that we've assigned to each of the 7 phrases in the Shadvad. So for ASCII, true, we're saying that a statement is true if it is true in every context, or if it doesn't require context to be true. So there's just no doubt that it is true. So it's objectively true or provably true from other true statements. And you'll notice that I used capital T true for the truth value and small t true for our understanding of the word true. That's for any mathematicians out there. An example would be, the average temperature measured across the world in 2020 was hotter than the average temperature measured across the world in 1970. This is objectively true. We can take all the measurements of 2020 and all the measurements of 1970. We can average them and we'll discover indeed that the average temperature measured in 2020 was hotter. False is exactly the opposite of true. It's false. A statement is false, capital F, if it is false in every context or doesn't require context to be false. An example would be the average temperature measured across the world in 2020 was colder than the average temperature measured across the world in 1970. Again, this is objectively false. We can take the temperatures that we measured in 2020 and those that we measured in 1970, take the averages, and we will discover, of course, that in 2020 it was hotter. So this would be a false statement. True and false. Now, true and false, we're taking to mean if it's true in at least one context and false in at least one context. I should have explained context at the beginning, sorry. Truth values have to be understood in the context of time or speaker or audience, place, intent, other contexts. So in the case of, like, let's say in the time context, in 1965, the statement Navin is married to Ina was certainly false. But in 1975, it was true because by that time, Navin had already married Ina. So over time, the truth value of a statement could change. If we're looking at the speaker context, when Moneesha, when I say Navin is my father, I'm speaking the truth. But when Navin says Navin is my father, it's the exact same statement. He is speaking a falsehood because Navin is not his father. So it depends on who is speaking, whether a statement is true or not. A place context, another example, if we're sitting in Canada and we say it usually snows in January, this is true. But if we're sitting in Australia and we say it usually snows in January, this is false. So Dad will continue.
The unknown, indeterminate, a vector, is unknown. The average temperature measured across the world in 2020 was hotter than the average temperature across the world in 2020. The truth of this statement is unknown. It could be known if we knew we had measured every single temperature in every place on Earth in 2020. Next. ASCII or other problem. It is true in at least one context and unknown in at least one context. In 1400, the true value of the statement, it is possible to construct a machine that can fly humans in the air across an ocean, was unknown. Today, it is true. False and unknown is exactly the opposite. In 1400, the truth value of the statement, it is not possible to construct a machine that can fly humans in the air across an ocean, was unknown. Today it's false. Next. True and false and unknown. I can lift a weight of 100 pounds. The truth value of this is unknown till I try to do it. When I try it and fail, the truth value is false. After doing a workout for a year, if I try it and succeed, the truth value will be true. Next.
I'll give some mathematical examples of the truth values. So syad ASCII, true, we're associating the truth value true. X is equal to X. This is always true. 2 equals 2, A equals A. This is always true. Nasti, false. X is not equal to X. This is always false. 2 is not equal to, that is a false statement. True and false. Now this is one where we look at context. So 10 plus 10 equals 100. This is false in base 10 because 10 plus 10 equals 20, but is true in base 2 because 2 plus 2 equals 4. So 10 plus 10 equals 100. Avaktavyam, indeterminate. So 0 over 0 equals 0. This statement is indeterminate. We don't know if it's true or false because the thing is 0 divided by anything equals 0. So we might claim that 0 divided by 0 equals 0. That's true. But on the other hand, anything divided by 0 is approaches infinity. So then we might say, well, 0 divided by 0 can't be 0. So maybe this is false. Or X over X, anything divided by itself is 1. So maybe we should say that 0 divided by 0 is 1. So this is absolutely indeterminate. We don't know what this is. Then there's ASCII and Avaktavyam, so true and indeterminate. So X divided by X equals 1. Now this is definitely true on the interval from 0, but not including 0 up to infinity. Anything divided by itself is 1. But in R, in the real number line, R includes 0, of course, and 0 over 0 is indeterminate. So this statement is both true and indeterminate, given the correct context. Similarly, for false and indeterminate, X divided by X is not equal to 1. So this is a false statement in the positive real number line. But this is an indeterminate statement in R because at one point in R, i.e. X equals 0, it is indeterminate. The final one is true and false and indeterminate. So I gave the example of a function defined on, I don't know how that became a theta. Oops, it's supposed to be a 0. So I gave the example of a function defined on different parts of the number line. So in the negative real numbers, we're going to define f to be equal to x. F of x equals x. Then at 0, that should be a 0. F of x is equal to 1. And when x is greater than 0, f of x is 1 over x. Okay, so you can see that the graph here is drawn f of x equals x in the negative reals with an open circle at 0 because this does not include 0. At 0, f of x equals 1, so I put a nice big dot on 1. And then, after in the real number, in the positive reals, f of x is going to be equal to 1 over x, and it's not a perfect curve there, but anyway, you can see that it essentially, goes up to infinity on the y-axis and up to infinity on the x-axis. So, so as x approaches infinity, f of x is approaching 0. So, but what is the limit? Sorry, I should have put a limit of f of x. This should say f of x in here. Limit as x approaches 0 of f of x. What would that be? Well, I mean, in the function is defined across all the reals, but it looks like the limit is 0 if we're just looking at the negative reals. If we're looking at the positive reals, the limit as we approach 0 looks like infinity. But if we're looking at 0 and we didn't look anywhere else but at that point, it would seem to be 1. So this this is the limit is equal to 0 is true if we're looking at the negative reals. The limit equals 0 is false if we're looking at the positive reals, and the limit equals 0 is indeterminate if we're looking at the whole real line. And
Okay. I'm going now to go to mathematical examples, same as binary values. If we assign in a bipolar system 0 and 1 to avyaktam, to nasti, and to asti, then we have a very interesting thing. This is the binary. I've given you 1 to 7 on the left, and on the right, you have 0, 0, 1 in the same order as it comes. And you can see that the 7 2s are presented in numeric order. In the binary representation are the decimal numbers 1 through 7 in order. We don't know if the omniscient meant it that way, but that is how it comes in my way of presenting in binary, the 7 truths. 1 to 7, we call it in binary 0, 0, 1 to 1, 1, 1, assigning the values to the 3 different main items, asti, nasti, avyaktam.
And I'll just point out that, we used E for exists. So asti is exists. Nasti, we used N for not exists or nasti. And we used I for indeterminate. So that's how we got these letters. And when it says only asti, then only E gets a 1. And there's no nasti or there's no avaktavyam, so there's zeros in these 2 spots. And similarly for all of the elements of this yadvad. So I just wanted to show yet another way of looking at these elements. The first phrase in this yadvad is syad asti. So let's just draw this circle to represent all of the possible true statements, or all of the existent things in the world, however you want to consider it. And you can see I've labeled it with 001 because the asti turned out to be 001 in the previous slide. And then we can draw the set of all the nasti. So let's say everything that's not existent or everything that's false, however you want to interpret it. Let's just take a look. So the green circle would represent the second phrase, syad asti. Syad nasti. And in fact, I've placed these numbers very carefully because we might say that only the green part represents the second phrase of syadvad, but the in-between part could be both asti and nasti, right? This third phrase, and we know it's third because this is 3 in binary. So this is the true and false, or present and not present. It could be the contradictions in the world. It depends on your interpretation, but the point is that, perhaps we say only the properly like red or pink part is asti, and the green part is nasti. And then this in-between part is like a brownish color or whatever. This is the asti and nasti. Then we add in the unknown, avaktavyam, right? Again, this blue circle is meant to represent sort of all the unknown things, but you can see that there is an overlap. I've drawn it as with an overlap between unknown and asti, like avaktavyam and asti. So this is the fifth phrase of Syadvad. And again, it's convenient that these line up as number 5. So perhaps this sort of purplish thing could be considered the asti and avaktavyam, true and unknown, or present and unknown, present and indeterminate. And similarly, this section here could be could represent the nasti and avaktavyam. Again, this is number 6. And then the intersection of all 3 circles, of course, would be the asti and nasti and avaktavyam. So perhaps these are the contradictions that are not known to be contradictions in the world, right? So it's true and false and unknown. And, you know, I said, like, perhaps this is false but not known to be false, and true but not known to be true. Now, we actually don't know if this is what the world looks like. I mean, for all we know, all the things that are true are also false. Perhaps the true and false, or the asti and nasti, should be on top of each other. Or perhaps we don't really know anything, and this unknown should be on top of everything. But this is, or it could be that they're completely disjoint, right? Perhaps there are no contradictions in the world, and therefore there should be no overlap between the red and the green. And then this 0, 1, 1 would certainly be empty, right? Because there's nothing there. We don't know. This is a representation, and you know, it has, at least it shows the possible interpretations of the Syadvad. This is again another interesting way of looking at the Syadvad. I've called it a state diagram. It's very reminiscent of computer science state diagrams, and I've labeled the states as 1, 2. This one is 4, and you can see, you know, I've put the binary number that corresponds to, like, the first phrase of the Syadvad. So this would be asti. This is the state 2, corresponds to the second phrase, which is nasti. This is state 4. So this corresponds to the 4th phrase, which is avaktavyam. And I called these simple states because they are only true or only false or only indeterminate. There's no ands in there. And I kind of have these arrows going in both directions. So when we think of state diagrams in computer science, we usually think of a state changing. And so in the context of time or speak or whatever, it is conceivable that you know, the state could change. So I just represented that, that, you know, could change from 1 to 4 to 2, whatever. Then we have the slightly more complex state, state 3, which is asti and nasti. So you can see that I put the arrows going from state 1 and 2, so asti and nasti. And you can also see that if you did an OR on the 2 binary numbers, you would get this number. So the first bit, or the first digit, is 0 or 0, so that's going to give us a 0. The second one is 0 or 1, so that would give us a 1. And the third is 1 or 0, that would give us a 1. So if you did an OR on these, you would get this. Similarly, if you did an OR on states 1 and 4, you would get state 5. And you can see bitwise, if you do the OR, you really do get 101. And that's the same thing, if you do an OR on states 2 and 4, you get state 6. And again, I'm kind of saying that in these states, perhaps as contexts vary, we can move from state to state, without, I don't know, I'm just conjecturing that perhaps movement among these states is possible. And again, if you take any two of these more complex states and you do an OR, you will get state 7. So any two of these, it doesn't matter. So that's why I put them all there. Then this is the most complex state, asti and nasti and avaktavyam. But what it means, I like this because it also is reminiscent of lattices. If I had drawn it the other way, we would have had something that looks a little bit like inflatus. I'm not sure, but anyway, Dad might have some other comments.
Well, the interesting thing about the state diagram is the fact that I would like the audience to interpret this in terms of the migration of soul from a simple state of nigoda to the most complex state of human being, or the state of being in moksha. Or we can talk of the migration of the solar system or Earth in the different phases of its movements around. It's a challenge to the audience now, the august listening audience, to come up with their answers at the end of our talk, see if they've got any answers for that.
So the next slide, I wanted to take a look at decidability, basically, and at the different complexities of problems in computer science. Some people may recognize this little, it's a Venn diagram, but it shows the different complexity classes as subsets of each other. But you can see that there's an equal sign and a question mark over each one. We actually don't know, and this is one of the big unsolved problems in computer science. Is P equal to NP? That's the big one. P equals NP. Is it true or not? We just don't know. And I'll just go through what these are. This is non-deterministic logarithmic time. This is polynomial time. So problems that can be solved in polynomial time would be in this group, in this set. Problems that can be solved in non-deterministic polynomial time would be in this space. Problems that can be solved in polynomial space, so they take up more space, and this usually talks about parallel computing and all, would be in here. This circle represents exponential time, so problems that can be solved in exponential time, and then the biggest one here is exponential space. These can also be thought of as context. Now, it could be that there are problems in the world that are decidable, regardless of what space you're looking at, or they're just simply decidable. And some of them will return an answer of yes. Typically, we ask the problems as yes/no problems in computer science. So among the decidable problems, we may say that, some of them are, well, we definitely can say that some of them are answered as yes and some are answered as no. So I kind of break it up into asti and nasti. And then it could be that regardless of context, there are some that are semi-decidable, in the sense that they are unknown, but the answer would be true if we knew it. Or they could be unknown, but the answer would be false if we knew it. Or these could be considered a section, or at least some subset of this could be considered a section of non-deterministic reasoning in some space, in one or all of these spaces. And then it could be that in the world, there are some problems that are simply, we don't even know if they're decidable. So we don't know if they're decidable. We don't know if they have a truth value of true or a truth value of false, or possibly they are contradictions. There are some that we just don't know. But what I actually like about this is that we can place this structure almost within any one of these spaces. So we could take, you know, ASCII and NASTI, like, could be those that are decidable in polynomial time. And then these semi-decidable could be those that are verifiable in non-deterministic polynomial time. And then this top thing, ASCII and NASTI and Avektavyam, could be absolutely undecidable in any kind of polynomial time. So there's so many different interpretations, but I like this. I like this view of the Syagvad, that, you know, that there's that hint at the fact that there are some problems that are simply unsolvable. And of course, the most, you know, famous one probably is the halting problem, which states that there is no program, there's no way to write an algorithm that takes a given description of a program and an input to that program and returns a value of yes, this stops, or no, this will never stop, like this program will run forever. This is called the halting problem, and it's proven that it simply cannot be done. So, and then of course, any problem that you can reduce the halting problem to is also completely undecidable. And Dad will continue.
This is just a list of the binary logic meaning. Binary, because we are going to talk a little bit later about three-valued logic. Binary is just 0 and 1. You're saying 0 to no and 1 to yes. And this is just a table. So ASCII, say logic 1, NASTI, we say logic 0, ASCII, NASTI, logic 0 or and logic 0 and 1. A vector, it is infinite, like a resistor or a diode. ASCII, a vector, it is there, it has a facilitator reaction as well as an indeterminate reaction. NASTI, a vectorium, is not, and not indeterminate. It's not there, but if there can also have an indeterminate reaction. And the last one, if it is there or not there, it is indeterminate action. Next. Now, I'll give you an example here of ASCII in a transistor. This particular transistor, BC547 transistor, it can work in two different ways, but right now I'll give you the ASCII example of it. It works as an example to find out if the current exists or not. It works as an amplifier. It takes in a tiny electric current at one end and produces a much bigger electric current at the output. In other words, a kind of current booster, but also allows you to find out if the current existed in the first place. Next.
We use the tilde to indicate not. So like not 1 gives a result of 0, not 0 gives a result of 1. A not gate in electronics inverts the input. So if there was current, it inverts it and it becomes there's no current. And if there was no current, it inverts and there is current on the output.
In mathematics, I've demonstrated it in APL and in Agni in Hindi there. We assign the value of 0 and 1 to or A. What is there in there is 0 and 1, shunya or ek. Negate it with the form, which is a symbol negation, nastia, and we get the result 1, 0, the opposite. So that is what
sorry.
it is.
Okay. And then this shows the chip 7404. It's a hex inverter. And it does exactly that. It in fact has 6 NOT gates in it. So the pins 1, 3, 5, 9, 11, and 13 are inputs, and you know it on each of those there could be a live wire or not, and the pins 2, 4, 6, 8, 10, and 12 are outputs. So whatever is input gets flipped, and if there's a 1 in the input, 0 will be on the output. If there's a 0 on the input, a 1 will be on the output.
It's a perfect example of nasty logic. It's used extensively in electronics. And now here is an electronic expression, SAD ASCII, Chanasti. The same transistor that I showed before can also be used as a switch. ASCII, Chanasti. The transistor is a semiconductor device used for amplifying or switching electronic signal. This particular transistor, BC547, acts as a switch between the collector and emitter. If the base of the transistor is given enough current, the switch closes and the current flows from the collector to the emitter. Here is a very extensive APL type of example. In the variable C, I have assigned a lot of negative values and a lot of positive values. You can see what I have assigned there in C. Now, when I divide it by 0 in APL language and in Agni language, these are the results we get. Infinite, everywhere. It says divide by 0 gives infinity to all those values. Syad avyaktavyam. Asti, alternate meaning of Syad asti cha avyaktavyam cha. If you take any positive number or 0 and keep on adding 1 to it, they say you get the next number in the next positive integer till you reach infinity. So there will be a point in time when you reach infinity. This interpretation is compatible with astronomically high numbers such as Krodakrari, etc., profuse in the Jain scriptures and literatures. Nasticha avyaktavyam cha. It is not and also indeterminate. By the same token, if you take any negative number or 0 and keep on subtracting 1, we are supposed to get negative series of integers. You get all it is negative till you reach infinity. This also is compatible with astronomical high numbers such as Krodakrari, very profuse in our literature. The wheel of time is divided into 2 half rotations This is per serpene or ascending time cycle, and our serpene, the descending time cycle occurring continuously after each other. The state of man and earth at any given time is either known and getting better, or known and getting worse, or indeterminate. More input is needed from you all on this aspect of my interpretation.
Now, 1 second. Now I'll talk a little bit about three-valued logic. This, again, it's so interesting and so very reminiscent of the Syadvad that we couldn't overlook it. So in three-valued logic, or 3VL, well, there are many systems of three-valued logic, but essentially each one of them has truth values of true, false, and some indeterminate third value. Which is obviously in contrast to bivalent logics like our classical Boolean logic, which obviously only has true and false. So in the three-valued logic, we're going to have F, U, and T, false, unknown, and true. And we have the same connectors, the same operations. So you can do a not A. So if A was false, then not A will be true. If A was undetermined, then not A gets a value of undetermined. If A was true, then not A is false. You can do and. Obviously, if these are the possible values of A, possible values of B. If A is false and B is false, of course, A and B will be false. If A is false and B is undetermined, again, false and anything is false, so it's going to be false. And similarly, if A is false and B is true, false and anything, so false and true is going to be false. Similarly, if B is false, it doesn't matter what A is, it's going to be false, right? And the only way to get a true value, of course, with and is if both are true. So if A and B are both true, and then the other values determine if both of them are undeterminate or unknown, or if one of them is true. So if A is undetermined and B is true, then it's still like unknown value. The connective or works very, really just how you would imagine it. If A is true, doesn't matter what B is, the result will be true, because true or anything is true. Similarly, if B is true, it doesn't matter what A is. So false or true, it's going to be true. Unknown or true, it's going to be true. Okay. And exactly opposite to and. The only way for or to be false is if both values are false. So if A and B are both false, then A or B has a value of false. But if A is undetermined or unknown, and B is either, so then the only way to get undetermined is if one of them is, if both are undetermined, or if one is undetermined and one is false. So or I should say unknown or false. So if A is unknown and B is false, unknown or false, we get a value of unknown. And unknown or unknown, we get a value of unknown. We can do exactly the same thing, assigning a value of -1 to false, 0 to unknown, and +1 to true. Then we get like negative, like a true negative A. This doesn't have to be a not symbol anymore. It could be a minus. Naturally, the negative of -1 is +1. The negative of 0 is 0, and the negative of +1 is -1, right? And corresponds to the minimum of A and B. So it and corresponds to intersection or inf. So this corresponds perfectly, and you'll see that these values, if you had changed this to all the -1s to F's, all the 0s to U's, and all the positive ones to t's, they would look exactly as we saw in this slide. Similarly for A or B, this is max, this is supremum, this is union, and again, this looks exactly like the OR diagram. You just take the maximum. So if A is -1, but B is +1, what's the maximum? +1, which is true. If A is 0 and B is 0, what's the maximum? Okay, 0, which is unknown, unknown. Now we're taking a look at, so Lukasiewicz is one person who, if we can mute, if one of the co-hosts could mute people who are muted, that would be great.
क्या चीज
In
क्या
fact,
चलने दो
do that.
करो तो
Right, so implication is actually defined as standard implication, so not A or B is, I should have written that down, but anyway, not A or B is the definition of implication. And then you can actually sort of rewrite A or B as A implies B implies B. And if you worked it out, if you were to sort of say not A, or like A implies B is the same as not A or B, and then A implies B, so you would take a not of this first and of the antecedent, and then or it with the consequence, you would find that you would actually get A or B. This is straightforward classical logic. But it also works in the three-valued logic. So if you were to assign like an unknown truth value to A and let's say false to B, and you worked out this side, you would find that they give the same truth value. And this is actually just a standard definition of if and only if. This is the same as classical logic. But the interesting thing is in three-valued logic, you can define a few more unary operators. So it is not false that A. So if like, let's say A is the statement, Truro is in Nova Scotia, okay? So that actually is a true statement. M of A is, it is not false that A, and it is equivalent to, I mean, it's in fact defined as not A implies A, okay? Now, this not A implies A is actually a falsehood in classical logic, but in three-valued logic, it can have the value of true. If A is unknown, then M of A is true. If A is true, then MA is true. Oh, sorry. Yeah, this is not always false. Sorry, I shouldn't have said that. It is usually false. Anyway, then the next unary operator is it is true that A. So again, let's say if A happens to be the statement, you know, all pigs fly, which is actually a false statement. L of A, you know, it is true that all pigs fly, but all pigs fly is a false statement, right? So what the definition of L of A is not M of not A. So M of not A in this case would be M of a true statement, which would be true, and then not would be false. So if I said it is true that all pigs fly, that is by definition, by this definition, a false statement, which is good. And then we have an I of A. So I is another unary operator. It is defined by M of A and not L of A. And then you can see the truth tables over here. These are so interesting because it allows us to kind of almost assign like operators to parts of the Siadbad. I mean, it's not perfect, but one thing that is really interesting is a couple of tautologies. A tautology is a proposition that's true everywhere. So it's always true. For example, A implies A. This is always true in classical logic. And it's also always true in three-valued logic. Okay. A, if and only A, if A. Again, this is always true. It's a tautology in classical logic, and it's also a tautology in three-valued logic. However, there are definitely some classical tautologies like A or not A. So, you know, either Truro is in Nova Scotia or it's not, right? This is always going to be true, right? But in three-valued logic, it doesn't have to be true. And then there's a law of non-contradiction. So we know that like A and not A, you know, in classical logic, we would never say, you know, Truro is both in Nova Scotia and not in Nova Scotia. Not a great example, but we would never say all pigs fly and no pigs fly, right? But then if you take the negative of that, it becomes a tautology, because this part here is always false. So the negative of that, or the not of that, is always true. This is, again, not a tautology in three-valued logic, but using that indeterminate, so the operator that says it is unknown that, if you use this operator, you can actually rewrite these classical tautologies as tautologies in three-valued logic. So it is actually true that, you know, A or unknown of A or not A, this is actually a tautology in three-valued logic. And you can see that the only thing that we added is the or of I of A to the law of excluded middle. And over here, all we do is we've got the A and not A inside the brackets, but we and a not I of A in there, and you'll see that that the inside of here has to be false, and therefore when you negate it, this whole thing has to be true. And you know, the fact that we get things like asti and nasti and something like avaktavyam, you know, to me, it's very interesting. Of course, it doesn't line up exactly, but I think there's a lot to be studied here. Okay, so go ahead, Dad.
There have been many interpretations of the three-valued logic and multi-valued logic since the Clausewitz. The subject is too vast. However, I would like to note that one of the popular database software called SQL uses three-valued logic. This particular aspect of interpretation requires a lot of further discussion beyond the scope of the present presentation. Many thanks to you all for listening to us, father and daughter, patiently on the unique subject of mathematical interpretation of Syadwad. Jai Jinendra.
Hello. Navin Mehta and Moneesha. Am I audible?
Not very.
Am I audible?
Just about, yes.
Am I audible?
We can almost hear you. Jiva Jain, if you could
Okay,
mute
Dr.
yourself, then we can hear Dr. Surendra.
It's noisy there. Purvi, you just mute everybody.
Yeah, we got it.
I can't hear anything. Somebody speaking or not?
No, I think Dr. Surendra Singh,
No, I have already
Okay.
muted everyone.
I think he wanted to ask a question or something.
I just want to congratulate you. No question. I will try to understand it in detail, but the Venn diagram